Okay, so last speaker with Handley will talk about PolySwyft, a sequential simulation-based nested set.
Cheers. So again, the graveyard slot's not ideal. To gather your attention very briefly, let's do a bit of interactivity. Before I start though, just to credit Killian and Christoph, who've been doing a lot of the work with me on this, and I'm really presenting mostly Killian's work. So, hands up if you have made a triangle plot ever. I'm sure I'm good. Hands up if you've written your own MCMC sampler. Hands up if you've used nested sampling. Okay, good. This is a good audience. Hands up if you've written your own nested sampler. I count one. Okay, right. Jose up there. Okay, so I'll just take you through the brief. So this is going to be a slightly more conceptual talk, although hopefully it should complement Maximilian's quite well in terms of different ideas on what I view as being the future of how we'll all be doing inference in the near future, and why this is important in particular for cosmic tensions, as this workshop has, or this conference has been centered around. So in the first instance, we'll go through briefly what we mean by likelihood-based inference, which I'm calling LBI, in an attempt to kind of distinguish it from SBI, which Maximilian talked about last time. In general, you first of all define a prior, and if you've got time, you spend it being philosophical. You then sample that posterior using a tool like Multinest or MC or Kabaya or Cosmosis or something else that you might use, and then you make some triangle plots. And if you've got a lot of computing power, you might then compute some Bayesian evidences to do Bayesian model averaging, as we heard earlier in the day. Here's an example of DesY5 doing this earlier in the year and doing all of that, including talking about tension quantification using a variety of different tension metrics. So this is contrasted with, and then just for notationally, that's Bayes' theorem, because there's a lot of P's, thetas, and D's in a rather sort of mouthful. We give them names, so we call that posterior, likelihood, prior, and evidence, and I will label these as P, L, pi, and Z, and then that obviously comes from this thing here, and I only mention this because as a proof of Bayes' theorem, this highlights the middle bit, which is the joint distribution, the Maximilian just mentioned. This thing here, which is P of D, comma theta, the probability of everything. All right, so what do you do if you don't know what the likelihood is? And this is why it used to be called likelihood-free inference. People didn't like that term because it makes it sound like snake oil. Of course, you can't really do inference without a likelihood. This idea of knowing the connection between data and parameters is absolutely key. But what really we mean is if you don't have an explicit expression for the likelihood, but in fact you have an implicit way of doing it. So one way of doing this is with what's called a simulator or a forward model. Now that simulator might be a really sophisticated pipeline, like the one we saw for kids in the, just in the last lecture, or it might be something a bit more straightforward, or it could be even real data. So LIGO are using their actual data stream to train their simulators, or as a simulator to train their simulation-based inference. The principle is that if you compress your of order a few dimensional parameter space, which will be this theta here, so this axis here is parameters, and that might be 6 dimensions if it's a cosmological one, and this here is D, which ideally would be of order a few thousand dimensions if it's a CL spectrum, but usually most things at the moment need to undergo a lot of compression, as we had last time with this score compression. If you choose a theta, you can then use that to generate example data sets, and if you choose a different theta, say from a different prior, you can use that to build up parameters from a joint distribution. And over time, you can populate that joint distribution. So in general, simulation-based inference is based around the idea that although you don't know what the likelihood is, if you have a generative model, you can populate that joint distribution, that probability of everything, and use that to learn what the posterior, the evidence, or the likelihood might be. So the key point there, and at the moment, that learning is done using machine learning, usually neural networks, but it doesn't have to be, and in fact my group's research, amongst other things, tries to remove machine learning to show that actually this is a much more generic method that will be carrying with us for many decades to come. The idea there is that once you've got those samples, you would learn the joint, or maybe the evidence, or maybe the posterior as that way, so you get some nice things here. These slides are all online, including the tech and the Python that generates them, so if you would like to pinch them for your own SBI slides, please do. At this link here, we'll hand that there gives you the slides there. Okay, so why is SBI useful? First of all, it's the usual case that you don't have a likelihood. It's only C and B where you have a well-defined, easy to calculate, and by easy, I mean it takes armies of French men and women decades to compute the Planck likelihood, and that's how long it takes, right? But beyond C and B, once you move to the collapsed nonlinear universe, you don't have a likelihood. And if you want to do, say, Bayesian inference on F1 cars or nuclear reactors or other things like I do in my spare time, this is very hard to do. So it's only the C and B where you know what the likelihood is. So that's, first of all, it broadens the application of SBI, of all the Bayesian goodness that we know. People often claim that it's faster than likelihood-based inference. In reality, this is just because in general there's a lot of emulation in it, and the neural networks are quite fast. If you speak to Alessio, he will tell you a lot about how actually you can emulate things in the likelihood-based method just as well. But the key point for this talk, or for this conference, is that in SBI, in principle, you don't need to encode fiducial cosmologies. This is the hidden gap in the armor of most of the analyses that we do as cosmologists, that most analyses at some point need to assume some fiducial cosmology to get to a good answer, usually just from pure computational reasons, and that's why SBI hopefully frees us from doing that. But the main reason why you should all know about this is that in general it's much easier to apply SBI because you don't have to spend years knitting a likelihood. You just literally take your simulator, which is one of the first things a scientist does when they're trying to understand a system, and then plug it into something that just takes in a set of simulations. This means just from raw evolutionary principles, SBI will come to dominate over LBI over the next few decades, whether or not it's the better way to do it. So we better understand that it's doing the right thing. The short answer is we're using SBI and cosmology a fair bit, certainly for weak lensing, but we don't see it in many CMB analyses because most of those data analysis codes were built before a generative paradigm, i.e., at the moment, it's very easy to kind of, as you're building your new weak lensing pipelines from scratch, to build in this idea of simulating mock data sets as you go along. But simulating night skies with foregrounds and cut skies and things like that takes a lot of work. Not as much work as it would be to rebuild a full likelihood, but still it takes a lot of work to do that. And amongst other things, that's one of the things I'm working on. But yeah, here's a list of things. I would also say that 2024 has been the year where it's really been started to apply to real data. Okay, in terms of what this talk is about my forays into a specific blend of SBI, in particular trying to combine neural ratio estimation with nested sampling. So I better sort of define both of those. So as I said, the general principle you should bear in mind is that if you have a forward model, you can generate samples from the joint distribution. If you can generate samples from the joint distribution, you can then try and learn various inference quantities from that true distribution. And these come in various flavors. They all begin with N, because at the moment all the state-of-the-art is achieved with neural networks. And then you can either do neural posterior estimation, neural likelihood estimation, neural joint estimation, or neural ratio estimation. For reference, the last talk was neural posterior estimation, I believe, Delphi's LP. Oh, is NLE, yes, Delphi is, the L in Delphi is density estimation likely for inference. Okay, so the NRE is, it often feels like a big sleight of hand. The principle is you generate joint samples, as I said. You can also generate samples from the prior and the evidence. And what you do basically is you consider the joint distribution, which is this little purple one here. So that's the joint smudge. And you can also generate from this separated distribution, which is the pink smudge. And if I gave you a sample, and I'll do my best to point with this bizarre accelerometer here, and ask which of those distributions does it come from, you would say that one has almost certainly come from the pink distribution, whereas that one has probably come from the purple distribution, but there's a small chance it could have come from the pink distribution as well. You train a classifier, like you would usually take a classifier and train it to classify cats or dogs or various types of faces or things like that as you do, i.e. using all of that machinery that's kind of in Machine Learning 101. And from that classifier, via almost magic, but not quite, you can get out this quantity that's the ratio, i.e. this ratio of the likelihood to the evidence, or by Bayes' theorem, the ratio of the posterior to the prior, or in general, the joint over the separated distribution. I won't spend a huge amount of time, but if you want a Bayesian proof that doesn't involve introducing some weird extra categorical variable, this is quite a neat one that kind of really rephrases it in terms of mold comparison. I'll just kind of highlight why I like NRE. And this is quite a subtle point, but for those of you that have spent some time thinking about this is probably quite an interesting sort of set of observations. So first of all, I think the link between classification and inference is pretty profound. It's quite a deep one that we're still trying to understand, that actually finding the link between parameters and data being equivalent to classifying things is very powerful. And in general, the bigger one, though, is that most of the progress in inference over the past 50 years has been avoiding density estimation. So if you think about your default Markov chain Monte Carlo samplers, where you wander around the parameter space with a random walk, taking ratios of probabilities, in general, you want to avoid doing density estimation. So it's a bit embarrassing that the state-of-the-art in SBI is achieved by using the latest and greatest density estimation tools for machine learning. NRE divides out the densities and the hard-to-calculate parts. In terms of why I don't like NRE and what I aim to improve by using nested sampling is that practical implications usually can only work in very low dimensions, so they work by restricting themselves to marginal plots, and they really only work with truncation mechanisms and, so that's basically that. Do it all right. So here's the state of the art in neural ratio estimation as it stands. It's the main sort of bit of code that does this is called Swift. I don't know if you know what Swift stands for, but it stands for Stop Wasting Your Precious Time, initially. And this is Christoph Fenniger's sort of brainchild, basically, that's been built up over a very long time. This is generally what Swift tends to look like, is that you basically do an iterative approach that we heard of a little bit of for the LFI approach that Maximilian mentioned, whereby they sort of have a refining process that aims to sequentially update things and do active learning to improve their training samples. So the idea is that you sort of try to focus your parameters onto a subset of the prior, which is usually a box. And this in general is, and the only way, the moment that this is achieved is by looking at pairs of parameters at time. This picture looks very similar to nested sampling. So I saw some hands up of people who've used nested sampling. In terms of the details of how it works, it's a bit different from the usual random walk that comes out of either a Hamiltonian Monte Carlo chain or a Metropolis Hastings chain. You start by sampling everywhere. You then throw away the points that are at lower likelihood value and repopulate at higher likelihood value. So over time, you find your live points start contracting around the peaks of a distribution. This is good because it means it's generally, these things are quite good at sampling from distributions with multiple peaks. That's one of the main use cases of nested sampling. But in particular, because it contracts probabilistically at a constant rate each time, it exponentially zooms in on the peaks in a way that allows you to estimate the density of states. So this is one of the real reasons why nested sampling is quite unique. It gives you a partition function calculator. But that's a little bit too detailed. The key point I want you to understand is that these look very similar to each other, i.e. this picture of TMNRE, which is truncated marginal neural ratio estimation, looks quite similar to nested sampling. And my aim for this work I've been doing for the past year with Kilian and Christoph is to take the TM out of TMNRE and replace it with NS, i.e. nested sampling neural ratio estimation. Before I do that, so obviously how you achieve this process is quite challenging. Here is the current zoo of nested samplers. I don't think I'm missing a few actually. This is a slightly out of date slide. But in general, nested sampling is distinguished by how you repopulate those live points. I can answer questions on that at the end if you're interested. And I will emphasize this, because this diagram is very hard to make. If you look at this, this is the picture of the discarded points that come out of a nested sampling run. You start by sampling uniformly over the space, but those points start to zoom in on some central region. If you zoom in on that central region, you find the points continue to concentrate further and further, and it does this in a self-similar way, which gives a scale invariant distribution focusing in on the region of interest. And this is very good for active learning, because it basically is the distribution that you want if you wanted to say, I'd like to cover the tails, but I also want to focus on that region, and I want to do that smoothly in between the two of them. This has been used in a fair different ways, and this is called the dead measure, which I think would be a good name for a Bayesian band. Right. So why it's hard to do SBI with nested sampling, and why it's taken me about a year with Kilian and Christoph working on this, is that nested sampling has a likelihood really hard-coded into it, in that at each iteration, when you want to repopulate those live points, you have to be able to generate a new live point from the prior subject to a hard likelihood constraint. So that likelihood is there, And that's precisely the thing that we don't know in simulation-based inference. We don't know the likelihood, so how can you do that? This is particularly difficult because if that learning is sequential, it means that the likelihood shifts, and if the contour shift, nested sampling is not very good at doing that. But I will highlight the DNest paper by Brendan Brewer and Dan Foreman-Mackey of MC fame, which is a truly remarkable paper that's very undersold in my view. In section 10, right at the bottom, they have nested sampling for approximate Bayesian computation, decade ahead of us, so very impressive. And then ANRE, which is autoregressive neural ratio estimation, which is Christoph's latest version of that. Okay, so here is how you do nested sampling and simulation-based inference at the same time. You start by drawing live points from the prior. You then simulate some data. You do your usual data generation process from those live points in this case. You then run NRE on those live points, or on those sort of that discarded run, and that will give you a rubbish neural ratio estimator. It will be not very good at all. But then what you do is you run nested sampling on that neural ratio estimator, which gives you a set of new dead points that concentrate around the region that that neural ratio estimator thinks is important, and then you repeat that process, feeding those back into one another as you kind of basically build up a set of dead points that gradually learn where the peak of the neural ratio estimation is. And in practice, this here, which is the general procedure of doing sequential simulation-based inference with nested sampling, you could plug in any nested sampler and any neural ratio estimator into that. But in this case, we use Polychord and Swift because that's what Polychord is my nested sampler and Swift is Christoph's nested sampler, but you could swap any of those out if you wanted to. And then just to kind of emphasize, this here shows this working, and that sort of the red is the true region, the true distribution here that's a 5-dimensional mixture Gaussian. So this is a hard problem. This isn't just a Gaussian problem. This is a mixture Gaussian for a given data set. You then start with the prior, which is in blue. At round 0, you are effectively at the prior. At round 2, you have a slightly rubbish neural ratio estimator with slightly rubbish posteriors, and then as time moves on and as you iterate over that, you gradually converge onto the true distribution. So this is the way of basically doing that. And what's impressive about this is that in this case, you are doing it in this problem in 5 dimensions with 100 data points. And that is therefore in contrast to a lot of the other existing software out there. Most other things need much more aggressive data compression than this, and other neural ratio estimators can't do 5 dimensions. They can only do 2. And in order to diagnose convergence, you basically have this idea where you either track the compression, and when that compression levels off, you converged, or you track the sequential compression, and when that levels off, you've also converged. And that gives you 2 things that's relatively robust. And you can see you've got the right answer in about 6 iterations, and if you run for 15, it's then stable. Okay, I'm going to finish there about 2 minutes ahead of time because we've all been here for long enough. So just to summarize, this here is therefore an instance of something which can perform neural ratio estimation on 6-dimensional parameter spaces in of order 100-dimensional data points, which makes it quite suitable for modern cosmological applications where you're fitting a ΛCDM model with slightly unknown compression. The idea is to push this further and understand the limits and strengths of how far this can go, and hopefully there'll be an imminent paper which will be post-Killian's thesis hand-in of order a month, plus or minus 1. And I'll also highlight this package here, which again, if you want to go and pinch any of these slides or any of the tech or any of the Python that makes these plots, this uses this package here, which is my linear simulation-based inference package that I've been building for a while. All right, many thanks.
So if I understood the nested sampling correctly, so what it does is it basically first identifies peaks kind of in the distribution, and then it zooms in and tries to explore those regions more. Is that correct?
Not quite. So it learns the peaks along the way. So the peaks come out at the end of the algorithm. You don't need to identify them first.
Can you just explain this a little bit more?
Sure. So you start by drawing live points all over the space. You then find the lowest likelihood points and throw them away. That gets you to there. You then find the lower likelihood points in that set and throw them away, repopulating each time. So the live points maintain a roughly constant number of points in that region, but you're always throwing away low points and replacing them with points at higher likelihood. And at the end, you're left with this set of discarded dead points that has found the peaks by slowly compressing, but exponentially compressing.
So would this method be affected by, like sometimes you can start with a distribution that does not really represent the target distribution, and regions, some regions may be identified as low probability regions, but as you sample more and more, you might realize that
yeah, so it kind of relies on the fact that topologically, the higher regions are always inside what you found so far.
as in, does it rely on our judgment of like how good of a handle we have on the distribution, like
so
the proposal scale, like, for example?
The short answer is no. And one of the reasons why people like nested sampling, it's very good at doing unknown distributions that you haven't seen. And what in practice people often do on an unknown problem is they'll run a nested sampler, and then once you've got that, they'll use that to create a distribution for a normal Metropolis Hastings sampler or something similar. So it's expensive, but it's terminally expensive.
Yeah, very short question. Why KL divergence? Why is that a very important metric here? Nothing else.
I mean, anything would do. The KL divergence is the most natural Bayesian/information theory reason to use. I mean, it drops out of Bayes' theorem as the Occam penalty, basically.
Okay. So you're not assuming anything is Gaussian or such?
I mean, that's why one would use a KL divergence, right? Because it doesn't need to assume Gaussianity. It's just a posterior average over a set of samples. And you've got posterior samples.
Thank you of the talk. I'm wondering, since maybe in the last slides, you say that Swifts only can have around 6 parameters. Why we cannot improve that? Since maybe nested sampling can have much larger parameter space, but why only 6 here?
So it's quite subtle. The reason is actually to do with one of the plots that Max showed when he was saying we were you had a very high likelihood, and you had this distribution of chi-squared values, and showing that we were in that chi-squared values. It's connected to the width of that distribution, i.e. the distribution of log R's over the posterior, in general, will have a value that's about the number of parameters over 2 from the peak, and it will be about the width of root the number of parameters over 2, i.e. 6 dimensions gives you something that's got a sort of -5 to 5 region, and neural networks are only able to learn a certain dynamic range in terms of log R. So this is a very busy slide. There's a lot of insight here that's not in the public literature anyway, but if you are interested in why that happens, this is my best understanding as to why that is at the moment. So it's a fundamental limitation, and a different algorithm would need to be created in order to ascend beyond 6, in my view. But I've got ideas. So.
Hi, nice talk. Thank you. So I wonder have you tried to, for example, run UltraNest or whatever nested sampling algorithm and compare the evidence with the evidence that you can obtain from your method, or you cannot compute the evidence yet?
It's a good question. So one of the reasons I'm not completely happy with this is that this doesn't give you an evidence, because what a ratio estimator gives you is not the likelihood, but the likelihood to evidence ratio. So if you want to get evidences, you need to use the evidence networks that Niall Jeffrey had a paper on last year, where you kind of basically treat model comparison also as a classification problem to get Bayes factors out. So you would need to do a second step where you use evidence networks to do model comparison. This doesn't. The evidence that you get out is useful, but not for model comparison.
Okay, and let's say that in ring-lensing, I'm sure that my likelihood is Gaussian, for example. So with all the steps that you mentioned, do you think I should go with the likelihood inference or your likelihood pre-inference?
How sure are you that your likelihood is Gaussian?
Let's say, I'm just imagining the situation, if you have to also run another algorithm for the evidence, what is more convenient at the end of the day?
This or nested sampling, or?
Yeah, with a nested sampling with a likelihood-based inference.
I mean, if you have a likelihood, it's hard to see why you shouldn't use that likelihood. But
if I have large parameter space, for example, would this be faster in the case you can increase your n? Or not necessarily?
Not necessarily. But in general, if you actually have a likelihood that you believe, I would say that would always be the best way to solve any problem. But the problem is that I don't really believe any likelihoods other than the C and B ones.
So there's no acceleration advantage here. It's just the likelihood you have it or not. Okay,
Yeah.
thank you.
Cheers.
Let's thank Willie.